from 4:30 to 6:30 p.m. Okay. O zaman haftaya çarşamba da çalışma için ders yok arkadaşlar. Normalde o saatte yapacaktık ama. Bugün işlediğimiz yere kadar sorumlusunuz. 4 tane soru olacak. Tamam mı arkadaşlar?
Tamamdır hocam.
Soru var mı?
Part mı olacak? Yani yarım saat şeklinde mi?
Evet, yani soruları teker teker vereceğiz.
Ekranda kalacaklar mı?
Yani PDF şeklinde size vereceğiz. Download edersiniz oradan.
Anladık. Kameralı normal bildiğimiz
Evet,
yazılı
evet.
sınav. Tamamdır.
Aynen. Any other question? Okay. Then let's start with our lecture today. Okay, so we're going to start a new chapter called Fourier series. So we have a few Fourier transform, but prior to learning the Fourier transform, we need to learn Fourier series. So today's lecture is going to be about Fourier series. So it has 3 types of Fourier series. We will start with the first type, which is called trigonometric Fourier series. I guess you don't see my screen.
No, we don't right now.
Okay, let me share it. Can you see it now?
Yes, we can, sir.
Okay, let's start. So we said the first type is called trigonometric Fourier series. Okay, let's start with first. Remember, we classify the signal at the beginning of this semester as a periodic signal or versus aperiodic or non-periodic signal. So let's remember what was the definition of a periodic signal. A signal f of t is a periodic under what condition? If f of t is equal to ft plus capital T0 for all t values. So this is the condition for the periodic signal, if you guys remember. So what's the T0 in this case? The smallest value of T0 that satisfies or satisfying the above periodicity condition is the period of the is the period of the f of t. So there may be a many t0 value that can satisfy this condition. So what we call period is the smallest value of t0 that satisfied the above condition. So the smallest value of t0 that satisfies this condition is called period of the signal. Okay, a periodic signal, some property of the periodic signal, a periodic signal must be an everlasting signal. Everlasting signal. What does it mean, everlasting signal? A signal that starts at t equal to minus infinity. A periodic signal must be an everlasting signal. In other words, it must start at t equal to minus infinity. Let's give an example. So visually, this is an periodic signal. Let's call it f of t, t. And let's change the color to this 0. And so on. On this side, we have the similar one. So these each copies, they're equal to each other, and they replicate every t0, as if you are copying the same information over t0 and over. So this is one of this copy over t0. This is another copy, as if we are replicating, and this is another copy. As you see, the same information, the same signal is replicated every t0. So, and it goes to minus infinity up to infinity. So such signal is called periodic signal. Another property of a periodic signal, f of t can be generated by periodic extension of any segment of f of t of duration t0. So what does it mean? I can generate this f of t, the complete f of t, by periodic extension of any segment of f of t of duration of t0. So what does it mean? Let me show with another color. So that means if I take a segment like here, starting from here up to one period, which goes to here, right? So this is a t0 segment. If I replicate this part, cutting this part and putting here again, as you see, and putting this signal this port over here, another T0. So if I can generate this complete periodic signal by taking any extension of a segment of f of t over 1 T0 duration, and you're going to come up with the same periodic signal. That's another property of periodic signal. Another property which is very important, the area under f of t over any interval of duration T0 is the same. Mathematically, this means if I take a segment from A up to A plus T0,
Hocam paylaşımınız durdu bende ama.
evet, şeyler oldu. Ya bu dokunmatik olunca. Okay, let me share it again. Now, do you see it?
Yes, we can see it.
Okay. The T over interval of duration T0 is the same. What does it mean mathematically? I take a segment from A to A plus T0 and calculate the area under that is going to be equal to from B to B plus T0 f of t dt. So visually this means that let's say my A is from here. I start A plus T0. The area under this is equal to this, right, guys? Let's call this A1, area 1. Area 1 is equal to, I took T0, right? Let's change the color. Okay. Let's say this is my B plus T0. Another segment of has a duration of T0, right? T0. So this area is gonna be this, right? And this area is called A2 and this is called A1. So area 2 is gonna be area 1 basically. If these signals are periodic, if you take any segment that has a duration of T0 and the area under that is equal to, if you take another segment that has a T0 duration, the area under both region is going to be equal to each other according to this property of the periodic signal. Okay, so Fourier series can be applied to periodic signal. This is very important. So we can apply the Fourier series to only Fourier. That's why we start with the periodic signal, and the relationship with our series is given as follows. So Fourier series can be applied to periodic signal. Let's say is applied is applied to periodic signal. So the signal must be periodic in order to apply this Fourier series that we're going to learn. Okay, now let's start with the Fourier series. Remember a sinusoid from your high school math knowledge is given as follows. Is C times cosine 2 pi f0 times t plus theta is equal to, and we call this as a W0, which is radian frequency. Okay, this is called amplitude of the sinusoid. This f0 is called frequency in hertz. This theta is called phase of the sinusoid. And we can rephrase this sinusoid in terms of radian frequency, which is going to be equal to omega 0 times t plus theta. And this omega 0 is called radian frequency. Radian frequency. Omega 0 is equal to 2 pi f0. So this is the sinusoid. So how do you calculate the f0? f0 is equal to 1 over f0. And we call t0 as a period, if you guys remember. f0 is our frequency. And hertz, the frequency has a unit of hertz, the period has a unit of second. And n times f0 is called nth harmonic of the sinusoid of frequency f0. Now we are ready to introduce the Fourier series now. Let us consider f of t is equal to c0 plus n is from 1 to infinity cn times cosine n omega 0 t plus theta n. You know, this is periodic, and we're not going to prove it here. Okay. In this case, where W0 is equal to 2 pi f0 is called the fundamental frequency. And n times omega 0 is called nth harmonic. Okay, we can express a sinusoid in terms of sine and cosine, right? Remember, guys, from your trigonometry knowledge, we can express a sinusoid, which was, remember, cn times cosine n omega 0 t plus theta n, in terms of sines and cosines, right? How do we that? Cn times cosine n omega 0 t plus theta n is equal to, if you expand this, Cn times cosine theta n times cosine n omega 0 t minus Cn times sinus theta n times sine n omega 0 t, right? So I'm going to call this as an A of n, an, and I'm going to call this as a bn. So then my sinusoid is going to take the following form, which is going to be an times cosine n omega 0 t plus bn times sine n omega 0 t. So this is my new cosine, where is an is defined to be Cn times cosine theta n, and bn is defined to be minus Cn times sine of theta n. So if you want to summarize, as a result, therefore, you can write down any periodic signal f of t in terms of trigonometric Fourier series, which is given as follows: a0 plus n is from 1 to infinity an times cosine n omega 0 t plus bn times sine n omega 0 t. So this is called trigonometric Fourier series, and this is equal to f of t is equal to c0 plus n is from 1 to infinity Cn times cosine n omega 0 t plus theta n, and this form of Fourier series is called compact, which is the second type, compact trigonometric Fourier series, where what's the relationship between the compact trigonometric and the regular trigonometric, where C0 is equal to A0, okay, the Cn is equal to square root an squared plus bn squared, and the phase theta n is equal to arctangent inverse tangent minus bn over an. So if I obtain the trigonometric Fourier series, and then using the parameter of the trigonometric Fourier series, then I can convert this into the compact trigonometric Fourier series using this conversion equation, okay, which shows the relationship between the Cn an bn, C0 a0, and theta n bn an. So we can switch or convert from one to another one using this relationship. Okay, here one of the important things in the Fourier series, as you can see, guys, is to find the coefficients. What are those coefficients? So these are the coefficients that we need: A0, AN, and BN. Of course, the W0 is important. So we need to find out those. Okay, question mark. So the question is, how do we find out these coefficients and the fundamental frequency, W0? Okay. So the next topic is computing the coefficients of a Fourier series. A Fourier series. How we're gonna compute these unknown parameters? Let's start with the fundamental frequency, which was equal to 2 pi times f0, which is equal to 2 pi over t0, my period. So we need to first determine the t0, which is the period of your signal, and then plug into this equation in order to obtain this W0, which is fundamental frequency. Next is to find A0 coefficient. We're going to decide on this A0 using the following integration. 1 over T0, integration over 1 period of f of t times dt. So we are going to use this equation to determine on A0. Similarly, the other coefficients an is equal to 2 over T0, integration over 1 period f of t times cosine n omega z 0t dt. This is the equation that we're going to use. Similarly, this is the equation in order to find out the Bn coefficients, which is equal to 2 over T0, integration over 1 period f of t times sine n omega 0t dt. Okay, once you find out these coefficients, you are going to plug in back to this Fourier series, trigonometric Fourier series equation, and then you obtain your Fourier series. We also sometimes ask you to draw this Fourier spectrum. What is the Fourier spectrum? Fourier spectrum. There are two figures. One of them is the Cn versus W frequency, which we call amplitude spectrum. Figure 1. Now we have another figure 2. Now you draw the theta and phase versus the frequency, and this is called phase spectrum. And the combination of this is called frequency spectra. So if I ask you guys to draw the frequency spectra of your Fourier series, you're going to draw two figures. One of them is the first figure, Cn versus W, which is for amplitude spectrum. The second figure is theta n versus frequencies, which stands for phase spectrum, and the combination of these two figures is called frequency spectrum. Okay, so I guess now we are ready to do an example together. Okay, let's start with an example. Okay. Find the compact Fourier, because compact trigonometric Fourier series of compact Fourier series of f of t, and then sketch its frequency spectra, means amplitude and phase spectrum. Okay, let's draw the figure together. Okay, let's do it here. Our f of t is given this. This is f of t over t. Okay. And this is our signal that I'm gonna draw. Starting from here. And so on. Okay. So 0, pi, 2 pi, 3 pi, minus pi, minus 2 pi, minus 3 pi. Okay. The first question, is this a periodic signal? Yes. So how do we know that? Because this signal, one way to learn is you start from one point and you go up to another point. So you start from one point, and if you go hit to the same point in next cycle, then this is your period. So in this case, T0 is equal to pi. And you can do this one from here. You start from here and you go and you hit the same point as you see another T0. Similarly, if you go from here to here, is T0 and so on. Or you can start from here and you end up with the same, is going to be same. So this is how do you determine the period of a signal. Okay, solution. Let's solve it together. First of all, the period in this case is T0 is equal to pi. And after that, we need to find out the fundamental frequency F0, right? Which was equal to 1 over T0, means 1 over pi. And the unit is going to be hertz. And we can write down this in terms of radian frequency, which was the W0, 2 pi over T0. So 2 pi over pi, and the result is 2 radian per second. Okay, we found the radian frequency. Now we are ready to write down our Fourier series. F of t is equal to a0 plus n is from 1 to infinity an times cosine n w0t plus bn times sine n omega 0t. Remember, guys, that was the equation for the trigonometric Fourier series. So what are the unknowns in this case? The unknowns are a0, an, and bn. We already find out the fundamental frequency omega 0. So how we are going to find out the a0 and the an, bn? Using the equation that we just learned. So let's use this equation. A0, for the A0, it was equal to, A0 is equal to, and 1 over T0 integration T0, remember? F of t times dt. So which is going to be equal to 1 over pi from 0 to 1 period pi. And by the way, I didn't give the equation for this. And the equation for this is exponential minus t over 2. So our f of t is equal to exponential minus t over 2 times dt. So if you calculate this, you're gonna see that it's gonna be equal to 0.5004. This is our A0 that we determined. Similarly, AN was equal to 2 over T0 integration over 1 period f of t times cosine n omega 0 t dt. Remember, guys? So let's plug in the parameters that we know. 2 over 2 pi, 0 to pi, exponential times cosine to nt dt. So I'm not going to solve this. If you solve this, guys, you're going to see that the result is going to be 0.04 times 2 over 1 plus 16n squared. This is my an. Similarly, remember for the bn, we have this 2 over t0 integration over 1 period f of t times sine n omega 0 t dt. And this is going to be equal to 2 over pi 0 to pi exponential minus t over 2 times sinusoid to nt dt. Okay, so if you solve this integration, the result is going to be 0.504 times 8n over 1 over 16n squared. This is my bn. Okay. So actually, what now we are ready for the to obtain the Fourier series of this signal. Therefore, let's plug in all this value to the equation a0, an, and bn, and it's going to be equal to 0.04 times 1 plus n is from 1 to infinity 2 over 16 n squared times cosine 2nt plus 4n times sine 2nt. So that's our trigonometric. This is trigonometric Fourier series. But what I'm asking is, remember guys, was compact trigonometric Fourier series. So what was the compact trigonometric Fourier series? Remember guys, from the previous page, it was equal to f of t is equal to c0 plus n is from 1 to infinity cn times cosine n omega 0 t plus theta n. Now, what are the unknown parameters in this case? Or c0, cn, and the theta n. So we need to find out those using the a and bn that we just obtained, right? And this cn and the a and bn has a relationship that we just learned. Remember, guys? And so let's remember those relationship between cn, a and bn. So C0 was equal to A0, therefore A0 was 0.504. 0.504. So that's my C0. And the Cn was equal to, remember guys, square root of an squared plus bn squared. And if you take the square of an and bn and add them up, so the result is going to be 0.504 square root 4 plus 1 plus 16n square plus 64n square over 1 plus 16n square. And if you reorganize this, and the result is going to be 0.504 times 2 over 1 plus 16n squared. This is my Cn. Last one was theta and the phase information, which was equal to arctangent inverse tangent minus Bn over An, right? And if you plug in this, you're going to see that theta n is going to be equal to minus arctangent 4n. This is my theta n. Okay. So we had the three unknown parameters C0, Cn, theta n, and we decided on this. Now we are ready to plug in these results into the equation to obtain the compact trigonometric Fourier series. F of t is equal to 0.504 plus again 0.504. N is from 1 to infinity 2 over plus 16n square root times cosine 2nt arctangent 4n. So that is the compact trigonometric Fourier series that I'm looking for. Okay, are we done? No. The question says that first find the compact trigonometric Fourier series, then sketch its frequency spectra, which is amplitude spectrum as well as the phase spectrum. Now, the last question that we need to answer is to draw this frequency spectra. So the first one is amplitude spectrum, which was Cn versus frequency, right? Let's do it together. And the second one is the phase spectrum, which is theta n versus W. And that is this theta n frequency, Cn frequency. And the W, remember, was equal to what? Radian. Hold on, please. Okay. When W is equal to 2, 4, n is equal to 3 times 2, 6, 4 times 2, 8, and then 10, and so on. Similarly, 2, 4, 6, 8, and 10. So you're going to evaluate this signal for 0 actually. 0 start from here. Let's write down. 0 start from here. So for when the n is equal to 0, Cn is going to be equal to point. Let me change the color. So it's going to be 0.4 because of this value, right? And the theta in this case is going to be arctangent. If you calculate, is going to be 0 degrees. So this is minus pi, this is minus pi over 2. Okay, then we start with n equal to 1. If you put this n equal to 1, you're gonna see that. Okay, let's write down for all of them actually, so that you can see clearly. So I'm gonna expand this compact trigonometric series, Fourier series, for the different n values. So which is going to be f of t is equal to 0.504 plus 2.244 times cosine 2t minus 75.96 degree plus 0.125 times cosine 4t minus 8287 plus 0.084 times cosine 60, which is for the n equal to 3, minus 85 times 24 degrees plus 0.63 times cosine 8t minus 86.42, and so on. You can do up to infinity. So I'm gonna just draw this. So for n equal to 0, the Cn is equal to 0.504 and the phase is equal to 0, as you can see, guys. But for n equal to 1, which is the W is equal to 2, the amplitude is going to be 0.24, which is almost half of that. And the corresponding phase theta m, this is the theta 1, this is the C1. For n equal to 1, so it's going to be negative 75.96 degree. And for C2, theta 2 is going to be 0.125, and the corresponding is going to be 82 minus 8287. And then C3 theta 3 C4, theta 4. So let's put the C4, C3 for omega equal to 6 is going to be 0.084, and then the corresponding is going to be 80 minus 80, 85.24, and then it's going to be for the C4 is going to be 0.063, and the corresponding is going to be 86 minus 86.42, and so on. We can do for the others. So this is the amplitude spectrum as well as the phase spectrum of this signal. So if you want to summarize, that was our periodic signal in time, which was the exponential minus t over 2. And if you draw the spectrum of this compact trigonometric Fourier series, this signal is going to be looks like this. Okay. Any questions so far? Okay, let's have a 10 minutes break. Okay, we are back. So let's continue. Can you see my screen?
Yes.
Okay, so in the first lecture we learned how to determine the trigonometric Fourier series as well as the compact trigonometric Fourier series. Now we are going to learn the third type of Fourier series, which is called exponential Fourier series. Exponential Fourier series. Okay. Actually, we're going to extract this one from the compact Fourier series. Let's write down the compact again. Cn times cosine n omega 0 t plus theta n is equal to, we can write down this cosine in terms of exponential, right? E to j n omega 0 t plus theta n plus exponential minus j n omega 0 plus theta n, right? Which is going to be equal to, if you expand this one with this, Cn over 2 times exponential j theta n times e to j n omega 0 t plus Cn over 2 exponential minus j theta n exponential minus j n omega 0 t. I'm going to call this as a dn, this as a d minus n, where dn is defined to be Cn over 2 times exponential j theta n, and d minus n is defined to be Cn over 2 exponential minus j theta n. Now we are ready to write down our exponential Fourier series equation, which is f of t is equal to d0 plus n is from 1 to infinity dn times exponential jn omega 0 t plus d minus n exponential this. So we can even write down this in more compact form, like d0 plus n is from minus infinity to infinity, except n is equal to 0 because it's already here as a d0, dn times exponential jn omega 0 t t. So we can write down this as follows: f of t is equal to n is from infinity to infinity dn times e to jn omega 0 t. So this is called exponential Fourier series. In summary, let's summarize. The exponential Fourier series is equal to f of t is equal to n is from minus infinity to infinity, dn times exponential j n omega 0 t, where you know omega 0 fundamental frequency is equal to 2 pi over t0, and the dn coefficients in this case we're gonna find out using this equation: integration over one period f of t times exponential minus j and omega 0 t dt. So this is the things that you need to remember, guys, which is the exponential Fourier series. Let's have an example for this exponential series as well. Example. Find the exponential Fourier series of previous example. What was the previous example? F of t was equal to minus t over 2. You want to remember? That was the case, right? So I copy that. And let's throw it here. Okay, we copy it here, right? Okay. You remember this one, right? Find the exponential Fourier series of this previous signal, the signal in the previous example. Okay, solution. Solution. Okay, right. Let's write down the equation f of t is equal to, and it's from minus infinity to infinity, dn times exponential j and omega 0 t. So we have two unknowns, w0 and the dn coefficients. And w0 was equal to, remember guys, 2p over t0. And from the previous example, we found the period to be pi. and the fundamental frequency is equal to 2 radian per second, right? Now we need to determine the dn, which is equal to 1 over t0 from over an integration f of t times exponential minus j n omega 0 t dt. If you plug in the parameters that we know, 1 over 2 pi 0 2 pi exponential minus j 2 pi j to nt dt. So this is going to be equal to 1 over pi 0 to the pi exponential minus 1 over 2 plus j to n t dt. So if we solve this integration, it's going to be 1 over pi minus 1 over 2 plus j to n times exponential 1 over 2 j to n t from 0 to pi. So if you evaluate for these limits, the result is going to be this. dn. Okay. So let's plug in back to the original signal equation f of t. If you put it back, it's going to be 0.4504, and it's from negative infinity to infinity, 1 over j4n times exponential j20. So this is my exponential Fourier series. Let's evaluate for the different n values expanded to the series 1 plus 1 over j4 e to j2t plus 1 over 1 j8 j4t goes to the infinity. For the negative infinity or negative values, n minus 1 is equal to 1 minus j4 times exponential j2 plus 1 over j8 times exponential minus j4t goes to minus infinity. So, well, we need to draw the spectra of this. That's why we need a dn versus w, which is the amplitude spectrum, and the theta n, sorry, not theta in this case, is dn phase information versus frequency, and this is called phase spectrum. So let's do this one. For one of them, it's equal to d1 is equal to, actually, you can see from here. Okay, let's start with the d0. d0 is equal to 0.504, right? And the d1 is equal to 0.1 plus j4. If you convert this to the polar form, which is magnitude, sorry, the amplitude times the exponential, So dn is equal to amplitude times exponential j dn. This polar form, if you do this conversion for the n equal to 1, is going to be minus j 74.96. So this is my d1, and this is going to be d1 amplitude is equal to 0.122, and this is my phase information d1, which is minus 75.96. So for the n equal to minus 1, which is d minus 1, as you see, is going to be equal to this, which is exactly same amplitude, but the sign of the phase change. So d minus 1 is equal to 0.22, d minus 1 is plus 75.96. Similarly, let's do for the d2, which is equal to this 1 plus j8, which is equal to 0.0625 times exponential j 82.87. So the amplitude in this case is equal to this, and the phase, phase is equal to minus 82.87 degrees. And for n minus 2, d minus 2 is equal to similar result, except 1 minus j8, which is equal to this. The sign is different, 80.87. So the magnitude is same, but the phase is opposite sign, which is this, and so on. You can do for n to infinity. Now we are ready to draw the amplitude and phase spectrum. These are amplitude dn for different value of n, and this is for the phase spectrum. Dn is 0, 0. Okay, this is pi over 2, this is minus pi over 2. We have for 2, 4, 6, 8. Similarly, 2, 4, 6, 8. for the negative -2, -4, -6, -8. And we have -2, -4, -6, -8. So you're gonna put all these values that were just we did together in the previous example. For when the n is equal to 0, the d0 is equal to 0.504, right? And then for the 2 is equal to 0.22 and 0.0625 and so on. So this is symmetric, that's why we have this here, 0.122. Symmetric, we have this 0.0625. And then we have these values that goes like this. So it's 0, -75 point something, remember was 96. Then we have 82.87. We have the symmetric opposite is 75.96. And then we have plus 82.87 and so on. This is the exponential Fourier series of such signal in the example. Okay. All right, guys, that's all for today. Any question? So we completed Fourier series. Next week, we don't have any lecture. We have an exam on Thursday. And after that, we will continue on Fourier transform. All right, thank you, guys. You have a nice day.